Hello and welcome to the second example that demonstrates the application of Maxima and Minima in differential calculus to try and solve applicable problems. So we solved a problem yesterday concerning a fence in the previous video, concerning a fence that is supposed to be uh, fenced with with supposed to be fenced of 100 meters long, and we were able to see how we can use the concept of stationary points to find the maximum area possible that will be fenced by the wire mesh. So in this particular problem, we are going to still delve on the same issue, that is the application of the knowledge that we got from stationary points to try and solve the surface area, the radius of a tin, given the following information. So we're having that a closed cylindrical metal tin is to have a capacity of 250 ml. So that is the capacity. Basically, that is talking of its volume. All right. So if the area, of the metal used is to be a minimum, all right. So that we have already been given the statement. So we don't have to go ahead and find whether it's a maximum or a minimum. But if the area of the metal used is to be a minimum, all right, what should be the radius of that tin? What should be the radius of tin? So basically, by mentioning the fact that the area of the metal used is to be a minimum, we basically then understand, therefore, that we are supposed to use the concept of stationary points to try and solve this particular problem. All right, and we're supposed to solve it thinking of the area of the surface area of the cylindrical metal that will be used to cover the whole cylindrical metal tin, and give without making any wastage or of any sort. All right. So what would be the radius of the tin? All right. What would be the radius of the tin, of the closed tin, given that particular information there? So, because we're talking of surface area, then we are going to try and find the surface area, express the surface area of a closed cylindrical tin. The surface area of a closed cylindrical tin is usually given by 2 pi r squared. All right. So this is the area of the upper and the lower, circular shape of the cylindrical tin, all right. So the upper and the lower, all right. So 2 pi r squared. Pi r squared is, how we find the area of a circle. So 2 pi r squared. Then the area of the surface surrounding the two circles, circular shape of the cylindrical tin, will be given plus 2 pi r pi r l, 2 pi r l. Yes, plus 2 pi r, not L really, 2 pi r h, 2 pi r h. So the circumference of the 2 pi r for the circumference of the cylindrical tin, and h for its height. All right. So this is the formula that we use to find the total surface area of a closed cylindrical metal tin. This formula we use usually is 2 pi r squared plus 2 pi r h. All right, plus 2 pi r h. And so if we are supposed to find the radius of this tin, given that the metal used was minimum, all right, to close the cylindrical metal tin, all right, then we are supposed to find the first derivative. We're supposed to find the first derivative of this function here, all right, of this function with relation to, of course, the cylindrical tin. We're supposed to find the surface area of this function here with relation to the cylindrical tin, and then equate it to 0. But we cannot do that because we are having different variables in this particular function. So we are having two unknowns. We are having r and h, and we can't go ahead and differentiate with respect to one variable, and then h will be undifferentiated. So basically what this means is that we are going to have to first of all solve for the value of h, and we'll do that using the information that we've been given here. So we've been given the capacity. So we're being told that this closed cylindrical metal tin is to have a capacity of 2 pi r, 2 pi milliliters. So basically that is the volume. That is the volume of this cylindrical metal. And so we want to use that knowledge, that information that will be given, to substitute for the value of h, so that we have the whole function written as a variable of r. All right, as a variable of r. So we know that the volume of a cylinder, will be given by pi r squared. Yeah, pi r squared h. All right, we know that the volume of a cylinder will always be given by the formula pi r squared h. And in this particular case, we have been given the capacity already, of course, which is also the same as the volume of this cylinder, and we've been told that it's equal to 250 pi milliliters. So basically, we are going to equate our formula, that is pi r squared h, to 250 pi. All right, and so what we are looking to do, we are looking to write this expression here, 1, as a subject of h. All right, so that we have h, and then we can substitute the value of h into our function, into the star equation that I have up there, as you can see there. That is for the surface area. So basically what we're going to do, we're going to make h subject the formula here by dividing both the left and the right side, with pi r squared. So when we divide both the left and the right side with pi r squared, we are going to get 250 pi all over pi r squared. All right, over pi r squared. All right, so basically when you divide this by pi r squared, you're going to get h, and so this is what you're going to get on the right hand side, 250 pi all over pi r squared. And of course this boils down to h being equal to pi and pi simplify, so we're going to have 250 r squared. All right, and I'm going to call this equation 2, actually equation 2, not 3. I'm going to call it equation 2. So equation 2 here is an equation that gives us the equated value of h, and we found it by equating it to the what? The formula of getting the volume of the cylinder, basically. All right, which is pi r squared h, and then of course given the capacity that we were given here, the volume that we were given here, we've substituted directly, and now we can find the value of h for this specific cylinder that we're talking about, and we're saying that the value of h will be equal to 250 all over r squared. So we're going to come to our star equation, and where we have h, we're going to write it using, we're going to substitute it using 250 all over r squared. So substituting for h, in our star equation, all right, we are going to have that the surface area, all right, will be equal to 2 pi r squared. All right, so the surface area will be equal to 2 pi r squared, all right, plus 2 pi r into, so instead of writing h, we are going to put the value 250 all over r squared, You see that? We're going to put the value 250 all over r squared. And the reason why we're doing this is because we want to differentiate the surface area volume. Okay, we want to differentiate this function here. And remember, we couldn't differentiate it because we had two unknowns. We had r and h. And so we use the information that we're given about the capacity to find, to rewrite the whole equation with one unknown, and that is r. And so you can see right now that the surface area equation has been written using only one unknown, and that is r. Of course, we all know the value of pi. Pi is a constant. All right, so Now that we have this, maybe we can simplify this further. So note that our surface area, which I'm going to, our surface area is going to be 2 pi r squared plus, I just want us to simplify this. So this will be 2 pi, 2 pi into 250 all over r. So I've basically simplified the r's. Okay, I've basically simplified the r's, and so I can also go ahead and multiply that further. All right, and so I'm going to have it to be 2 pi r squared plus 2 times 250. That would be 500 pi all over r. All right, so that is our final. That is our final equation, and I'm going to call it equation 3. So for us to solve this particular problem, we are going to have to differentiate equation 3 and equate it to 0, of course, because now we only have one unknown, and that is r. So we can basically go ahead and find the derivative of equation 3. But before we do that, I want to write this term here, 500 pi all over r, in a form that makes a lot of sense. So basically, this here can also be written as 2 pi r squared plus 500 pi. And then whenever we are having a number all over r, we can always have it as r raised to negative r raised to negative 1. So this basically is our final equation here. So for us to find the derivative of this particular equation, we are going to have the derivative of this area, okay, SA, with respect to r, will be given by 2 times 2 times 2, of course, that will be 4. All right, that will be 4 pi. All right, remember this is also a constant, 4 pi. And so r will be 2, 2 minus 1, basically giving us r. All right, so that's the derivative of this term here. So it will be 2, which is the index of r, times 2, giving us 4 pi. Okay, and of course 2 minus 1 giving us r raised to 1 there. So plus, we would go ahead and write plus. We're just going to focus on derivating the second term. So the second term, basically, we're having negative 1 multiplied by 500. And so when you multiply that, it's a positive number and a negative number. It will be negative 500. It will be negative 500 pi. And of course, we are having that our r is raised to negative 1. So negative 1 minus 1 will be r raised to negative 2. Of course, negative 1 minus 1 will be r raised to negative 2. All right, so for us to solve this particular problem, we will go ahead now and equate the whole equation to 0. All right, so basically the equation, which now I'll call equation 4, for us to solve for the value of r will be equal to 4 pi r minus 500 pi r raised to negative 2 equals to 0. All right. Of course, this here is what we equated to find the the stationary points of the function. So this is what we equated to get the stationary points. Yes, to get the stationary points of the function. So notice that our aim is to find the value of r. Our aim is to find the value of r. And we're going to find the value of r from this particular equation here. Now, let me show you how we're going to do that. Yes, so we are having 4 pi r minus 500 pi r raised to negative 2 equals to 0. So I want to write it in a form that you will easily understand. Then it will be easy to relate to. Okay, then it will be easy to relate to. All right. So basically, this is the same as 4 pi r minus 500 pi all over r squared. All right, so basically r raised to negative 2 is the same as the numerator, that is 500 pi all over r raised to 2, and we are going to have that being equal to being equal to r0. So for us to do have a clean equation that has less complications, we're going to multiply all of these terms by the LCM of these terms independently, which is actually r squared. All right. So when we multiply all of them by r squared, we're trying to get rid of this denominator here. Notice we are going to have 4 pi r cubed minus, all right, 500 pi being equal to 0. So basically being equal to 0. So basically r squared and r squared, all right, so giving us that. So we can go ahead here and find and basically simplify all these two terms by dividing, okay, by dividing all the terms by 4 pi, as that is a common factor. Okay, so when you divide this by 4 pi, basically we're going to remain with r cubed, okay, minus, so 500 divided by 4 pi is going to give us, in a moment, it's going to give us 125. Okay, 125, of course, the pi will simplify, and so 125 equals to 0. So we then notice that r cubed will be equal to 125. Okay, we take the 125, negative 125 to the right hand side. And so basically for us to find the value of r, we basically find the cube root of the left and the right hand side. All right, so the cube root of this particular number here is actually 5. So basically that means that the value of r is 5. So we've solved the value of r here, and so we can emphatically say that the radius of this closed cylindrical tin will be equal to 5 centimeters. Will be equal to 5 centimeters. And so this answers the question of the the radius of the cylindrical tin if it's covered by a minimum surface, a minimum metal around its surface area. So that is it for this particular class. If you have any question, and if maybe you haven't understood this one, you can go and maybe replay the video again so that you are able to understand what we've actually done. And if maybe you're not able to get more clarification from watching the video, just drop a comment in the comment box, and I get back to you. Thank you and have a good one.